Good afternoon, ladies and gentlemen. My name is Tran Vu and would like to talk about my paper for EUMETSAT Conference 2021 entitled Using Machine Learning to Improve the Prediction of the Convective System Surface Field. First of all, this is the summary of the presentation including four sections. First, we talk about the multi-view of convective system by the DO. This means Sentinel-1 iris and geometrical versus satellite, then the relationship between the wingers and deep convection. We also present convective wingers estimation by Sentinel-1, C-band, SAR, and SMART, the L-band, the radiometer. Second, we illustrate the multi-view of result of convective system by the combination of Sentinel-1 iris and EUMETSAT. Third, we would like to show the initial result of the inverse estimation based on machine learning from the worst data. Finally, we talk about the conclusion and perspective. Now, this slide presents the 3D semantic observation of deep convection and vertical and horizontal dynamics. As you can see here, the hot air represented by the instant graph is contributed to the formation and development of the deep convective clouds. The hot air is then cooled and become heavier and finally move toward the surface. This is thus also called draft. If the thermodynamical conditions at the mid-level are favorable, the draft will become more intense. When they hit the sea surface, they may induce wingers that can be estimated from the data offered by Sentinel-1 and the other devices like radiometer or scatterometer. Now, thank you so much in improving of the EUMETSAT release and Sentinel-1. We can combine three devices to observe a deep convective cloud, intense data, and surface wingers respectively. So now let me talk about how to be able to estimate surface spectrum size and radiometer data. On the left, you can see here via radar signal, we can perceive backscattering or normalized radar recession from sea surface roughness that is strongly impacted by surface wind. The relationship between the surface wind and radar backscattering can be described through geophysical model function. In C-band, it's called the CMOD, and it's able to use CMOD and for surface estimation. And now on the right, the L-band smart radiometer instrument will measure brightness, temperature of the ocean surface also conducted by wind. The obtained data are used to calculate the difference between the brightness temperature of the ocean surface and that ocean surface which is not impacted by wind or low wind. Then the difference in brightness temperature is applied to the radiative transfer model to estimate surface speed. The detail of the two models can be found in the reference cited in our paper. So we have explained in the previous slide how to estimate surface spectrum size and radiometer data. Now we would like to talk about the estimation of convective wingers from SAR data. But first, why SAR data? Because they have advantages a high spatial resolution and wide swath that can offer the observation of convective wind pattern at various scales. For many years, the interpretation of the high intensity radar scattering outside image is an interesting debate scientific subject. Indeed, we can list here three assumptions to interpret the new feature. Rain effect on the sea surface or hygrometer in the melting layer or convective wingers up to 25-30 meters per second. Many papers in the literature have indicated that the C-band radar scattering is almost not impacted by precipitation, and then we can estimate surface convective wingers from C-band Sentinel-1 image. We are presented here to interesting Sentinel-1 image showing the presence of the surface convective wingers. They tend to move westward, as you can see here. Also, we like to say that the supply convective windows can be estimated from the L-band smart data. Not that everybody accepts that the L-band radar signal is not conducted by rainfall. And then the similarity between the risk estimated by L-band and C-band will strengthen our assumption that supply convective windows can be estimated from C-band Sentinel-1 image. Now we are moving to observe a mesoscale convective system. We see that the supply convective wind pattern on Sentinel-1 and deep convective cloud detected by EUMETSAT have the same location. Likewise, the corresponding ALICE data show the vertical wind representing turbulent zone at the mid-level with many intense downdraft and updraft. The missing data indicates due to the dense water clouds. In particular, the internal rough at the near sea supply match the Sentinel-1 wind hotspot and the coldest cloud section. When observing the MEDUSAT image from 1821 to 1976, we see that the deep convective cloud move very slowly, probably due to the low wind intensity at that level. Meanwhile, the coldest section changes very quickly. So now we are presenting here another case of mesoscale convective system observed by Sentinel-1 and EUMETSAT. This case is interesting because they can observe the wind prone and can assume that is the convective wind tend to move slightly southwestward. In fact, when we see the corresponding MEDUSAT image from the 1736 to 1821, we note that they also tend to move toward the southwest. The convective cloud in this case seem to move faster than those in the reverse case. They indicated in the reverse slide, in addition to Sentinel-1, we can estimate supply convective wind from the L-band smart radiometer data. Here is the observation of supply wind pattern on Sentinel-1 and smart image on the April 1st, 2017. This supply wind pattern is directed on Sentinel-1 image at about 5:14, while this one is observed by smart about 15 minutes later. Both of them have very close form. Despite having a larger spatial resolution, we can see here the strong supplying zone with about 15 or 17 meters per second on smart image. And when comparing the location of the supplying pattern on Sentinel-1 and smart image, we can note that this one tends to move southwestward. And they expected the convective windows on Sentinel-1 and smart image had the same location as the deep convective cloud detected by EUMETSAT. In particular, they also have the same displacement direction of the southwest. So now we would like to present the estimation of the convective windows by machine learning and depending from the race geo data. This work is based on the conclusion that convective windows estimated by Sentinel-1 and deep convective cloud detected by EUMETSAT have strongly. You can see here the GRACE data are used input data and Sentinel-1 images are used to train and validate the learning model. They may be gain, CNN, image, etc. The estimated figures are compared to the institute measure the institute data given by NOAA and Sentinel-1. The Gulf of Mexico is selected in this study because we can find easily the institute data from the GUI and to validate the learning model. So now we are presenting some initial results of the convective windows estimation. The two first images show the coldest cloud section below the 210 degree minus temperature. On the left, we can find the convective wind gusts estimated from Sentinel-1 image from 12 to 25 meters per second. The middle image to show the wind gusts estimated by the learning model from GRACE data. They are not exactly the same, but the location is very close. And on the right, we cannot find the wind gusts from the GFS data normally. The same learning model is applied in this case. the convective wing pattern detected on Sentinel-1 have the same location additive the convective cloud detected by EUMETSAT. The learning model can also predict convective wings at the same location. However, it lacks some wing hotspot and the wing pattern is smaller than that on the Sentinel-1 image. Now we are presenting the case that convective wingers is detected on one image. As you can see here, however, the learning model cannot predict wingers at the same location. On the contrary, this can illustrate that the learning model seems to overestimate wingers because the wings associated with deep convection on Sentinel-1. As you can see here, is not so high as that predicted by the learning model. No wing burst is detected on Sentinel-1 image, while the learning model predict a wing pattern at the same location as you can see here. So in conclusion, the combination of LEO and GEO satellite means one smart areas and EUMETSAT offer a 3D view of a convective system and also strengthen the semantic understanding of the deep convection, and particularly the assumption of the high intensity radar by scattering induced by convective wingers. Convective wingers can be estimated from C-band Sentinel-1 SAR and L-band smart radiometer data. Sentinel-1 data can estimate wind hotspot up to 25 meters per second and illustrate wind front. The current study proposed the use of machine learning beam to predict the convective wingers from the geo data. The obtained results show that this approach is promising. We can predict the wingers in some cases. The machine learning deep learning models still make error in some cases. For example, from positive with the wingers or from negative with the reverse. Therefore, the learning model needs to be improved. Thank you very much for your attention.